Why, hello. Today we're going to go on to section 15.3 that deals with partial derivatives. And you might be thinking, well, what on the heck is a partial derivative? You know, we did derivatives back in Calc 1 and Calc 2, but what's a partial derivative? Well, the whole idea here is you have a function, and right now we're only going to be dealing with a function of two variables. Towards the end of the section, we'll realize that it really doesn't matter if you've got 2, 3, 4, 5, 6 variables, 100 variables. We could ask, if you fix one of the variables, and then you let the other variable change, what is the rate of change of f of xy with respect to the variable that you're allowing to change? Now, to give you as a concrete example, and don't frantically sit, copying down everything, just sit back and watch what I'm doing right now. I'm looking at a chart. I have a chart right here, and I have we used this exact same table, I think, the other day. I stands for your index of what the temperature feels like it is presently. And your index of how what it feels like to you, whether it's hot or cold, what temperature it feels to you, is a function of what the temperature actually is in the room and what the humidity is in the room. And so, like, if you look at this chart right here, if I look at like when the temperature is 96 and the humidity is 70, it feels like it's 125 degrees. Okay. Now, what I'm going to do is I'm going to say, what if I fix the humidity at 70%? So I'm going to have a new function which I'm going to call g of t, and what it feels like to me is really only a function of the temperature because I fixed the humidity at 70. So we're just looking at this section right here, if you go down around that chart. Okay? So I could ask, what is g prime at 96? All right, now remember back from your Calc 1, Calc 2 days, the derivative, whenever you took the derivative, if you had a function, in this case, we have a function g of t, which gives us our index of how it feels. If we wanted to evaluate g prime of t, remember g prime, or any prime, gave you a rate of change, how your dependent variable changed with respect to how your independent variable changed, right? Like y prime was dy dx, how y changed as x changed. In this case, my index, I, which is a function of g, if I wanted to compute g prime of t, it's how does my index change as I change my temperature? So right now we're looking at g of t as being a function just of t because we're fixing the humidity at 70. All right, so if I wanted to figure out what g prime of 96 was, I would let h go to 0. And you probably remember this back from your Calc 1 days. It's the old f of x plus h minus f of x all over h. And so since we want to find g prime at 96, we're going to take the limit as h goes to 0 of g of 96 plus h minus g of 96 all over h. And since we had g of t equal to f of t comma 70, we're plugging in 70 in for our humidity. We'll have the limit as h goes to 0 of f of 96 plus h minus comma 70 minus f of 96 comma 70 all over h as h goes to 0. So in other words, what we're going to be doing is we're taking how the index changes over how the temperature changes and let the change in temperature go to 0 is what we're doing. Now, if I wanted to get a concrete idea using this chart of what g prime of 96 would be, all right, I actually could do it two ways. And let's see if I can, let me fold this paper just a little bit. So my function g, there we go, that should work. All right, now, what I can do, since we're doing g prime of 96, here, notice I have little squiggles because I'm estimating. Remember, g of t was f evaluated at t with the humidity at 70. So if I wanted to get an idea of what g prime at 96 is, at 96, my index of how it felt was 125. All right? And what I'm going to do here is I'm going to look at what is my index at 98. Okay? So we're looking at what's my index at 98 minus what's my index of 96. That's change in index, which goes here, 133 minus 125, all over. Now, where did the 2 come from? Remember, this is how my index changes over how my temperature changed. Well, if I'm going from 96 to 98, my temperature's changing 98 minus 96, which is 2. So using this data right here, trying to get an estimate of what delta I is over delta T, I end up with 4. Because 133 minus 125 gives me 8, and 8 divided by 2 is 4. Now, right now, I used this data right here. Let's instead use the temperature that's below 96. How about 94? So on the flip side, we could look at this data, and we're going to say, okay, well now I want to look at from here to here. So my delta I is 118 minus 125, and my delta T is 94 minus 96, which gives me a negative 2, and that over that gives me 3.5. So we estimated delta I over delta T by taking one temperature above it, and delta I over delta T by taking one temperature below it. And as you can see, since they're not equal, a very inexact science would be saying, why don't we take the average of the two, and that might even give us a closer estimate of how your index is changing as you change your temperature. So G prime of 96 is approximately equal to 3.75, just using our data chart. All right, now notice what we're doing here is we were estimating how your index changed as your temperature changed with the humidity fixed. We fixed the humidity at 70. Okay, and in fact, they should have a 70 here. I don't know why we have a 20 type there, and there should be a 70 here too. Okay, I apologize for that. I'll have to fix that. Okay, we also could do the following. We could look at, since the index was a function of temperature and humidity, we could fix the temperature at 96 and let the humidity change. Okay, so in this case, what I'm going to do is I'm going to fix my temperature at 96. So we're looking at this row. All right, and we're going to call this G. G of H is equal to the function of the temperature fixed at 96, and the humidity is H. And we might want to very well figure out what G prime is for this function. And that's exactly what I'm going to do next. All right, in fact, we're going to call this function big G, just to give it a different name. All right, so here I want to figure out what's G prime at 70. Now notice, G is your index. So if I want to get G prime of 70, I want to get a measure of how the index is changing as I change the humidity, because the humidity is my independent variable for this single variable function. So again, G prime of 70 is going to be the limit as H goes to 0 of G of 70 plus H minus G of 70. And in this particular case, G of H was F with your temperature fixed at 96. So it's going to be F of 96 comma 70 plus H minus F of 96 comma 70 divided by H, and letting H go to 0. Now with the chart that I just had, it's very inexact. You know, we just have it for discrete values. We know we don't have it for what happens when your temperature is 96.24 or something like that. But to give an idea, if we wanted to evaluate what is G prime when the humidity is 70, what we could very well do is we could say, oh, we're fixed at 96, so this is the value that we have when the humidity is 70. So why not take delta I over delta T for this set of values, and then why not take delta I over delta T for this set of values? That's exactly what I'm doing here. It looks very, very formal, okay? And in fact, notice the humidity that's, oh, excuse me, I'm not going this way. We're going this way because we're letting humidity change. We're going this way. So I could look at delta I over delta T here, 125 minus 121 over 70 minus 65. Or I could look at delta I over delta T as 130 minus 125 over 75 minus 70. And that's exactly what's going here. Computing your rate of change going one step below or one step above, I get these two values, and why not take the average? And again, what is this derivative giving me? It's telling me how my index is changing as my humidity changes with the temperature fixed, in this particular case, at 96 degrees. And this is what a partial derivative is. What is a partial derivative? Well, here's your definition. And you don't have to frantically copy this down. It's in your textbook, and we're really not going to use the definition that much anyway. All right, we'll find a quick and dirty way to do it. But notice what it says. Look at this. If f of x, y is a function of two variables, its partial derivatives are the functions f. Now, we can write it as f with a little sub x or f with a little sub y. That's not the only way that we write it. We'll find that there's many other ways to write it. For me to type, that was the easiest way to type, and that's why I typed it that way. It's defined by, now look at the definition. It looks, in fact, let's write our old definition. Our old definition for derivative was f prime of x was equal to the limit as h went to 0 of f of x plus h minus f of x all over h. Now, you remember doing that over and over and over again. Well, notice the partial derivative with respect to x lets x change and everything else remains constant. So notice y is not changing. We're looking at f of x plus h minus f of x, and y is fixed. On the flip side, if I wanted to figure out the partial of f with respect to y, we're letting y change and x does not change. X is fixed. Okay? Now, this particular notation, I probably don't use this the least. Little f sub x and f sub y. Okay. So coming over here, notations, partial derivatives. And the book sort of went wacky, but they listed every way that you can list it. This is pronounced the partial of f with respect to x. This notation I use the most. Okay? Partial of f with respect to x. Okay? That's like a delta symbol. And this is partial of f. You can also write it this way. If your function z is equal to f of x comma y, you could also write it as the partial of z with respect to x. Since x is your first variable in your list, you could also write it as f sub 1. If you're into linear algebra, a lot of times I like the differential operator. I tend not to use this at all, but big D sub 1 means you're differentiating with respect to the first variable. Or if you want to be more specific, differentiate with respect to x. All of these notations you can find in many different books. And what's going to happen with, you're taking Calculus 3 with me, but you very well could be taking differential equations down UD or someplace else, and you might have a professor that likes one of these notations over the other. So it's important for you to, to understand. And we also have the exact same notation with respect to y. Okay? All right, now how do you actually do a partial derivative? Like we spent Calculus 1, I think a month learning how to differentiate. How do you actually take a derivative, a partial derivative? It's very easy. To find the partial of f with respect to x, regard y as a constant and differentiate f of xy with respect to x. So if you're differentiating with respect to x, you're taking the partial with respect to x, you consider all the other variables to be constants. And what's the derivative of a constant equal? 0. If you want to differentiate with respect to y, it's the same way. You regard x as a constant. And this is for z in terms of f of xy. Well, if f was a function in terms of x, y, z, and w, if you differentiate it with respect to x, you would consider y, z, and w to be constants. Okay, so let's practice. Huge part of your homework is practicing, getting used to thinking of a variable as a constant when you're doing your partial derivative. Okay, so first example that I want to do. Determine the first partial derivatives of the function f of xy equals 3x squared minus 2y squared. Now, the first partial with respect to x, in your notes, I wrote it this way. I tend not to use that notation. It was just easier for me in terms of typing the visuals. I also could write it as partial of f with respect to x. Now, when I do the partial of f with respect to x, I think of y is a constant. So think of y as 25. Y is a constant. Y is not changing. So look, I say, I'm differentiating 3x squared with respect to x. Piece of cake. Bring down the 2. 2 times 3 is 6. I get 6x. Minus, what's the derivative of 2y to the 5th with respect to x? 0. Because y is a constant. In your head, pop a 25 in for y. The derivative of 25 is zippo. So this derivative is just 6x. Okay? What if I want to figure out the partial of f with respect to y. In that case, think of the other variable, x, is a constant, like 5. So the derivative of 3x squared is the same as differentiating 70, or 5 squared is 25 times 3, 75. Derivative of a constant is 0. Now I'm differentiating 2y to the 5th with respect to y. That's going to give me 10y to the 4th. And so my partial with respect to y is minus 10y to the 4th. It's that easy. But you do have to practice. My analogy is like, well, I always want to think, oh, Mrs. Strocko is going to get thinner, all right? So yeah, the keys to the kingdom are working out. My daughter's a big fitness nut. And I go watch her out in the gym, and I watch her, and it looks, I mean, it's easy. I think, why do you even bother doing that? What would I even get out of it, doing those sit-ups and lifting those weights? And then I get on the machine, and all of a sudden, you know, she has them like piled like here, and I can't lift it with just one little weight, because she's been doing it for a couple years. She's been practicing. Same thing with calculus. Mrs. Strocko's been doing it 30 years, heaven forbid. Then you can figure out my age, but I'm doing a long time, more than 30 years, to tell you the truth, probably 32 now. But what you need to remember is I've been doing it a long time, so it looks easy for me. You guys have to practice, because if you can't take a partial correct, the rest of the chapter is going to fall apart. So we need to practice. So let's do this one. Determine the first partial derivatives of the function f of x, y equals blah, blah, blah. So the first I want to do is take the partial of f with respect to x. So you notice the notation. You just have this little fancy d instead of your usual df dx. So I look here and I say, all right, I have 3x to the 6th plus 2x squared y cubed minus 5xy squared. The reason I crossed that out is that's just f. Now to take the partial of f with respect to x, it might help if you underline what's the constant. Y is a constant, y is a constant. All right? So if I'm looking at that as a y as a constant, notice I could look at this as 3x to the 6th plus the constant 2y cubed times x squared minus the constant 5y squared times x. You all with me? Because these are constants. So when I'm ready to do my derivative of 3x to the 6th with respect to x, bring down your 6. Yeah, Mrs. Strocko, I get 18x to the 5th, plus this is a constant, 2y cubed, and then you multiply it times the derivative of x squared, which is 2x, minus this is a constant, which is 5y squared, times the derivative of x is 1. So my answer is going to be 18x to the 5th plus 4xy cubed minus 5y squared, because y is a constant. Okay. Let's do another one. Same problem. What if I want to differentiate f with respect to y? Now just rewriting f, notice it's 3x to the 6th plus x is the constant, so think of it as 2x squared times y cubed minus 5x times y squared. Since we're differentiating with respect to y, this is a constant, this is a constant, this is a constant. So the derivative of 3x to the 6th is 0, plus 2x squared times derivative of y cubed is 3y squared minus 5x, because it's a constant, times derivative of y squared, which is 2y, which gives me 6x squared y squared minus 10xy. It's just an art form. Everything else but the variable you're differentiating with respect to is a constant. All right, this one. I just want to figure out f sub x. That's the partial of f with respect to x. So okay, if I'm differentiating with respect to x, let's underline what we're considering to be a constant. X is a constant. Oh, no, excuse me. Mrs. Strocko better copy it again. We're going g of xy is equal to x natural log of x cubed plus y squared. So if we're differentiating with respect to x, oh, here I have g and here I have f. I apologize. This should be a g sub x is what it should be, because it's the partial of g with respect to x. Looking here, the partial of g with respect to x, y is a constant. But notice now, you can't forget everything that you learned from Calc 1, Calc 2. This is a product, isn't it? It's an x times a natural log. And we're differentiating with respect to x, so unfortunately, yes, 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 we must do the product rule. So we're going to take the first, which is x, times, now what's the derivative of log u? 1 over u. times, what's the derivative of u with respect to x? So derivative of x cubed is 3x squared. Derivative of y squared is nothing. Plus the second times the derivative of the first, derivative of x is 1 with respect to x. So it'd be nice probably to clean this up a little bit. We can put this over 1, put this over 1. So why not write it as 3x cubed over x cubed plus y squared plus natural log of x cubed plus y squared. Can I cancel these x cubes? No. Calculus 3 people don't do that, because you only can cancel when they're glued together by multiplication, which gives you a form of 1. All right, we doing okay? And leave it like that. That's beautiful. That's fine. Okay, next one I want to look at is, oh, again, major typo here. It says determine the first partial of f with respect to r. No, 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 no. It should be g with respect to r of the function. And we have g of rs is equal to r squared times e to the s over r. That's my function. Now, since we're taking the partial of g with respect to r, which you also can write as g sub r, we are considering the s to be a constant. So it might be helpful to write this function as r squared e to the s times 1 over r. You with me? S over r is s times 1 over r, because that's the constant s times the function 1 over r. Now again, since we're differentiating with respect to r, we have a product, don't we? You know, your stuff from Calculus 2 hasn't gone away. So we're going to be using a u times a v. So the partial of g with respect to r is the first function r squared times the derivative of the second. Now what is the derivative of e to the u? E to the u times the derivative of u. So it's going to be e to the s over r times, now what's the derivative of s times 1 over r with respect to r? Good. The s is a constant, and the derivative of 1 over r is minus 1 over r squared, plus the second, which was e to the s over r, times the derivative of the first, which is 2r. Definitely you should do a little bit to clean things up. In this particular case, you have r squared times this times s times minus 1 over r squared. We can cancel the r squareds. So let's see, a negative 1 times s, I prefer to write that as a negative s e to the s over r plus 2r e to the s over r is our final answer. Okay, let's look at another one. Here's a function that's a function of 3 variables. H is a function of x, y, and z. And they want me to figure out the partial of h with respect to z. So again, we consider x and y to be constants. So this is like a log u, right? And we take the derivative of log u. It's 1 over u times the derivative of what's inside. Derivative of x squared is 0, because it's a constant. Derivative of y cubed is 0, because it's a constant. Derivative of 1 over z, if you think of it as z to the negative 1, its derivative is minus z to the minus 2, which I can write as minus 1 over z squared. And I guess if we wanted to, 1 times a negative 1 is a negative 1. And if I multiply the denominators out, I'd get x squared z squared plus y cubed z squared. And z times z squared, 1 over z times z squared is plus z. And that might be a little nicer. But, you know, multiple forms would be accepted. Question?
Yeah, can you also do the derivative of 1 over z as the natural log of z? Because it's 1 over u.
You're differentiating. When you have y equals log u, your y prime is 1 over u times the derivative of u. So this is going to be 1 over all of this times, and we got to differentiate this.
Okay.
Okay, so, okay, no problem. Let's do another one. Now this one, you don't even see this notation all that much, but I put it there because I think it's nice to see. Another way to write this is find the partial of f with respect to y evaluated at the point negative 6, 4. So this is a definite derivative, a specific derivative. We want to evaluate it when x is negative 6 and y is 4. So what we're first going to do is figure out what's the partial of f with respect to y? And you guys remember from your Calc 1 days, if you have y equals sine u, its derivative is cosine u times the derivative of what's inside. So that's exactly what we're going to do here. The partial of f with respect to y is, since we've got a sine u, it's the cosine of our angle times, we are differentiating 2x plus 3y with respect to y. Since we're differentiating with respect to y, x is a constant. So the derivative of 2x is going to give us a big goose egg. And what's the derivative of 3y? 3. So we can rewrite this as just 3 times the cosine of 2x plus 3y. Now, since they want me to evaluate this particularly at negative 6, 4, I want to evaluate this derivative at negative 6, 4, what I do is I plug in a negative 6 in for x. 2 times a negative 6 is a negative 12. 3 times 4 is 12. So what's 3 cosine of 0? And this is cropped up so much. Cosine of 0 we should know is 1. 3 times 1 is 3. So the particular derivative evaluated at that point is 3. Not hard. This is not a hard section. Now, we have higher derivatives. Just like we had higher derivatives in Calc 1, in Calc 3, it gets a little bit more exciting. You can have, nobody writes it this way, fxx. They write it this way. What this means is when you see this notation, you differentiate with respect to x, and then you differentiate with respect to x again. This notation you're going to see a lot, and you're also going to see it written this way and this way. But what it's saying is you take f and differentiate with respect to x and then do it again. Notice fxy means you differentiate with respect to x first and then with respect to y. So in this notation, you read from left to right. Differentiate with respect to x and then differentiate with respect to y. But notice in this notation, this means, when you see it this way, you differentiate with respect to x first and then with respect to y. You read it that way. So when you see fxy, differentiate with respect to x, then with respect to y. But when you see it this notation, you go this way, x first, then y. All right? So if you see fyx, you differentiate with respect to y and then with respect to x, because you read it that way. And this way, you differentiate with respect to y and then with respect to x. And right now, you're quite concerned, you know, oh, what if I get the order wrong? So let's look and see. Determine the second partial derivatives of the function f of xy, which equals x to the fourth plus x cubed y squared minus 3y cubed. Now notice, fxy means first differentiate with respect to x, and after you're done, take that answer and differentiate with respect to y. We are going this way. So to figure out fxy, first we have to differentiate with respect to x. So let's see, if I differentiate with respect to x, I get, let's see, if I'm differentiating with respect to x, y is a constant. So y is a constant here, y is a constant here. So we have the derivative of x to the fourth with respect to x is 4x cubed plus x cubed times the constant y squared. Y squared is just a constant. So that's going to be 3x squared times the constant y squared. Are we all okay? So to get the partial, now to get fxy, we take the partial with respect to x, and then we differentiate it with respect to y. See, first we differentiate it with respect to x, now we differentiate with respect to y. So since we're differentiating with respect to y, x cubed is a constant. So this is a 0. And what's the derivative of this with respect to y? Well, it's going to be the constant 3x squared times the derivative of y squared, which is 2y, and we get a 6x squared y. Okay. Now, they asked us, so we got f of partial with respect to x and then with respect to y is equal to 6x squared y. Now, unfortunately, they also want me to do fyx, so let's do that one. If we want to compute fyx, what we have to do first of all, remember it goes this way, we have to differentiate with respect to y first. So what's fy? Well, x to the fourth is a constant. X cubed y squared is the constant x cubed times y squared. Derivative of y squared is 2y. Derivative of 3y cubed is minus 9y squared. Now, to get fyx, we take this partial with respect to y, and we take the derivative of it with respect to x. So I look here and I say, the derivative of x cubed times 2y, it might be better to write this as 2x cubed y minus 9y squared. Since we're differentiating with respect to x, you bring down your 3 and you get 6x squared times the constant y, and the derivative of 9y squared is 0. So fyx, we got 6x squared y. You might notice the partial with respect to x and then the partial with respect to y is exactly as the partial with respect to y and then with respect to x. Mathematicians notice this, and a gentleman by the name of Clairaut, which I'm never going to test you what Clairaut's theorem is. In fact, I never knew it till this book. Nobody ever told me that it was Clairaut's theorem. I just knew that this was the case, all right? But it's nice to say, give credit to the gentleman that proved it. It says, suppose f is defined on a disk D that contains point AB. Notice this function is a function of two-dimensional, of x and y of R2. You've got some point AB. And they're saying, suppose at AB, you can draw some little disk around it so that the functions fxy and fyx are both continuous on D. In this case, these were polynomials. They're continuous over all R2, right? So if they're continuous, then it says, relax. It doesn't matter if you do partial with respect to x and then partial with respect to y, or partial with respect to y, then partial with respect to x, because you will get the same answer all the time. Okay, so it's nice. So sometimes if you forget this note, which am I doing first? Even though it's nice to remember, you go that way. If you forget, it doesn't matter, as long as they're continuous. Now, if I gave you one on the test where one of them was discontinuous, well, then they would not necessarily be equal. And that's when students come to me and they go, I can disprove Clairaut's theorem. What will happen is it's discontinuous at the point AB. All right, let's do this one. They want us to verify the conclusion of Clairaut's theorem. And the function is f of xy is equal to x times y times e to the y squared. And I chose this one because you can get a little confused when you're doing your partials. So let's first I want to get fxy. So I want to say, what's the partial with respect to x? Now, since I'm going with respect to x, all of this is a constant. This is like one stinking constant times x. So when you have a constant times x, your derivative is just the constant. Isn't that cool? You all with me? Because this is like x times some big old 5. Now, after we took the partial with respect to x, we want to take the partial with respect to x and then differentiate with respect to y to get fxy. And this is, Miss Strocko, it's just a u times a v. So it's first times derivative of e to the y squared is e to the y squared times the derivative of y squared, which is 2y, plus e to the y squared times the derivative of y, which is 1. So it looks like I get 2y squared e to the y squared plus 1. Okay, and I'm just going to copy that right here. Oh, excuse me, plus e to the y squared. I'm thinking of factoring out the e to the y squared, but no necessary. So let's see, I have fxy equals 2y squared e to the y squared plus e to the y squared. Okay, is what I got. All right, now let's do fyx. Okay, now what do we have here? We have f is equal to x, y, e to the y squared. So if I'm differentiating with respect to y first, notice you have a constant times a big old fat function. How do you want to, if I have a constant times a function, I like just to factor the constant out. Would that be okay? So I'm going to do that. Taking out my constant, I now have to, since I'm differentiating with respect to y, I have to differentiate this because it's a constant times a function. So it's a constant times the derivative function. So it's the first times the derivative of the second plus the second times the derivative of the first. So I have fy equals x times 2y squared e to the y squared plus e to the y squared. Now I want to take fy and differentiate with respect to x. Well, if I'm differentiating this with respect to x, this is just x times a huge constant. This is like a big old 52. Well, the derivative of 52 times x with respect to x is just the 52. So it's just the constant 2y squared e to the y squared plus e to the y squared. And as you can see, we just proved that fxy and fyx are one and the same. So as long as fxy and fyx are continuous, it does not matter in which order you do your derivative. Okay? And the ones I assigned for the homework that you practice, well, the reason you're doing it is you're practicing taking the derivative. Okay, a little bit more. How about this notation? These are higher derivatives. All right? Notice here my function is e to the xy times the sine of z squared. Now with this one, what is the order that we're doing? With this notation, remember, you read it this way. All right? So the first we are differentiating with is respect to z. So first we have to figure out what's the partial with respect to z. Well, since I'm differentiating with respect to z, what's this e to the xy? A constant. So I have the constant times derivative of sine u is cosine u times the derivative of u. So my partial with respect to z, I'm going to write it as 2 e to the xy z cosine of z squared. All right. So first of all, we took care of respect to z. What do you think this means here? It means do it twice, right? So we're going to differentiate with respect to x and then with respect to x. Notice this notation is the same as take f, differentiate with respect to z, then with respect to x, then with respect to x again. So first, we got to differentiate with respect to x. We take this and we want to differentiate with respect to x. Okay, now, since we're differentiating with respect to x, what's this thing right here? A constant. What's this? A constant. So when I differentiate and I have a constant times a function, my derivative is the constant times the derivative of the function. The derivative of e to the u is e to the u times the derivative with respect to x. What's the derivative of xy with respect to x? Y. And I prefer to write this as 2yz cosine of z squared e to the xy. It's nice to put the e to the xy last. Now we're not done yet. We did this one, we did this one. We got to differentiate with respect to x again. So differentiating with respect to x again, God is good. This is a constant. It has no x in it, does it? No product rule. So it's our constant times the derivative of e to the xy. The derivative of e to the u is e to the u times, what's the derivative of xy with respect to x? Y. And so my final answer is 2y squared z cosine of z squared e to the xy. Okay. All right. Let's put that one off to the side for a minute. Okay, let's do this one. A couple more things and then we'll be finished. F is a function of r, s, and t, where it's s squared times the natural log of r, s, t cubed. So we have, let's write this out, we have f is equal to s squared times the natural log of r, s, t cubed. And they want me to figure out the partial of f with respect to r, with respect to s, with respect to t. Remember, in this notation, we go this way. So first we have to figure out what's the partial of f with respect to r. Piece of cake here, all right. We have s is a constant. S is a constant, and t cubed is a constant. So this is going to be a constant s squared times, what's the derivative of log u? 1 over u times, now we're differentiating r, s, t cubed with respect to r. Perfect. Because it's the constant st cubed times r. let's see. This is a pretty nice problem. The s's cancel, the t cubes cancel. So we have the partial with respect to r is just s squared over r. Now next we have to differentiate with respect to s. So we're going to take this and differentiate with respect to s. Do you notice I could write this as 1 over r times s squared. You all see that? S squared over r you can write as 1 over r times s squared. So if you differentiate with respect to s, 1 over r is a constant, and the derivative of s squared is 2s. So we have 2s over r if we want. Then lastly, they want us to differentiate with respect to t. And all this for nothing, because if we're differentiating with respect to t, 2s over r is a constant. Our answer is 0. Okay? Now before I do my last example, I want to show you, you actually can do this on your TI-92 calculator. So let me just take this up for a second, pull it up. Let's pull this one up. Let's see. The function I want to look at, I'm looking for one that I've got it written out. Here. Looking at this function right here, I'm looking at the function f, which is equal to x times y times e to the y squared. Okay? And we wanted to figure out, here I did the function, the derivative with respect to y, and then we did the derivative with respect to y with respect to x. Just turning it on. All right, first of all, let me hit F1 and clear the whole thing. All right, and then just to be careful, since I didn't check this, option 1, 2, 3, 4, 5, F6, it says clear all my one-character variables. Maybe somebody using this before me defined x to be 2 or something, and I don't want that to happen, so I'm just going to hit enter to have that happen. All right, and then let's hit clear to clear that screen. Now the function I want to differentiate is xy times e to the y squared. So what we're going to do is notice the derivative keys right above the 8, right here, right above the 8. So I go Shift D. All right. The function I don't want to differentiate was x, no implicit multiplication, just like Maple, times y times e to the y squared. My e button is right above my ln button, and here's my natural log. Here's my natural log, so I go Shift ln, and I get e to the, and it's e to the y squared, y. Notice we don't have an x squared key on here. All right, now there's my function, xy times e to the y squared, and I want to differentiate with respect to y, so I just go comma y. Okay, and there it is. Notice they have the x in there. They have we had 2xy squared e to the y squared plus e to the y squared times x. Now if I want to differentiate that with respect to x next, I can go Shift D. I can take this up here and highlight it and hit enter. It pulls it down, and then I can say differentiate that with respect to x. Okay, and there's my final answer. Also, I think I got this right. Let me hit clear on this. And I'm just going to, notice I'm just hitting my arrow going up because I want to scroll that first thing that I put down here. Okay, notice that says differentiate with respect to y. But if I put comma x, it means differentiate with respect to y and then differentiate with respect to x. Okay, and as you can see, what's it say? Did it go a little wacko? It went a little wacko, so I guess we have to do it in baby steps. I apologize. Okay, I should have checked it before I went on camera. All right, but you'll find that the calculator is nice for checking yourself. The thing to be careful is when students get wrong answers, maybe using this for some other course, they stored x as being a 2. If you stored x to be a 2, x is a 2. So when you're trying to differentiate with respect to other things, they're plugging in 2's all the time, so you have to be careful. Okay, lastly, one more example, and then we will be finished for the day. Use the table of values of f of xy to estimate the values of the partial of f with respect to x at the point 3, 2, and the partial of f with respect to x at the point 3, 2.2. All right, so now remember, the first one I want to do is the partial of f with respect to x at 3, 2. Notice this is my x column, this is my y column, so here's my 3, 2. Now since we are taking the partial of f with respect to x here. It's how f changes as x changes, and what's being held constant? The y. The y is being held constant. So y is stuck at 2. So we're just looking at this column. Because you can see we're letting the x's change, but y is fixed. Y is fixed at y equals 2. All right, so we have two different ways that we can do this. We can get change in f over change in x using this data. And my f values are 22.4 and 17.5, so I can go 22.4 minus 17.5. And if I go this minus this, how are my x's changing? 3.5 minus 3. And I'll take the calculator up in a second to get that. Or I also could do these two values. So I would get change in f over change in x would be, how about 17.5 minus 10.2? And if I go this minus this, I got to go 3 minus 3.0 minus 2.5, which gives me both of these have 0.5 in the denominator. And I think I'll take out my calculator. I just brought this one because it's nice and simple and quick. So figuring out what this number is on the top, I have 22.4 minus 17.5. A numerator I get is 4.9. And if I take 4.9 and divide by 0.5, I'm getting 9.8. And for this one, I have parentheses 17.5 minus 10.2, and dividing it by 0.5, I get 14.6. So going to the left of x, or going below x and going below, we got two different estimates for how f is changing with respect to x at that particular value. And so our best guess would be the average of the two, 14.6 plus 9.8 divided by 2. And if I take out my trusty calculator, let's see, 14.6 plus 9.8 divided by 2 gives me 12.2. Okay, let's just do one more. In this case, we want to get the partial, how f is changing as x changes. So again, y is fixed in this case at 2.2. So the value 3, 2.2, 3, 2.2 is right here. Again, y is fixed. We're going to look at that column there, letting the x change, but y being fixed. And again, the partial is an estimate of how f changes as x changes. So if I take this one and this one, I would have 26.1 minus 15.9 over 0.5, and we'll figure out that number in a minute. And if I instead want to take the data on the other side of it, it would be 15.9 minus 9.3 over 3 minus 2.5 is 0.5. And taking out my trusty calculator, let's see, I'm going to go 26.1 minus 15.9, close parentheses, divided by 0.5, 20.4. And the other one's going to be 15.9 minus 9.3 divided by 0.5 gives me 13.2. And if I want to take the average of those two, I end up with 16.8. And that is a measure of how, what this is saying is, if I look at delta f over delta x, if I fix the y at 2.2, at the point when x is 3 and y is 2.2, if I change my x coordinate by 1 unit, I'm estimating that my f will change by 16.8. This is not a hard section. Let's practice. Oh, I apologize. I have one very important problem to do. We're not done. We have one very important problem to do. Let's do this one. Then we will get our homework assignment. All right. I forgot to do implicit. See, it's good I make these ahead of time, or you'd have homework and I wouldn't have done the problem. Just as in Calc 1 and in Calc 2, occasionally, your function was given implicitly, which in this case means x, y, and z are all mixed up. All right? Now, we are assuming that z is a function of x and y. You all with me? We are assuming that z is a function of x and y. what we want to do is we want to figure out what's the partial of z with respect to x. That's the first thing we want to do. We want to determine the partial of z with respect to x. Now remember, we're assuming z is a function of x and y. X and y are your independent variables. Z is your dependent. Now think, if you're differentiating z with respect to x, remember y is a constant. Z is not, because z is changing as x changes, you see? We're letting x change, and as we change x, z is going to be changing. So now, just as you did back in your Calc 1 days, we want to differentiate this with respect to x. So we want to differentiate x squared with respect to x. We want to differentiate y cubed with respect to x. We want to differentiate z to the fourth with respect to x. And unfortunately, we want to differentiate with respect to x 3x cubed y squared z with respect to x. And since I'm running out of space, what's the derivative of 12 with respect to x? 0. You with me? I have to differentiate each one with respect to x. Now, what's the derivative of x squared with respect to x? 2x. What's the derivative of y cubed with respect to x? Right, 0, because y is a constant. What's the derivative of z to the fourth with respect to x? We have to use the chain rule, people. Remember the chain rule? You can't differentiate z with respect to x, so what you're going to do is differentiate with respect to z, and then multiply by the partial of z with respect to x. Remember that? Because the z's cancel, so you really have the partial of z to the fourth with respect to x. So we instead have 2x plus 0 plus the partial of z to the fourth with respect to z is 4z cubed times the partial of z with respect to x. Because remember, z is not an x, so you take your derivative like you always do, but then you have to multiply times the partial of z with respect to x. Now we have to take the derivative of this with respect to x. It might help you to remember 3 is a constant and y squared is a constant. So you could write this as 3y squared times x cubed z. You like doing that better? Because this is a constant times x cubed z. So if I'm differentiating that with respect to x, I'm going to have 3y squared times, this is a product. So since that's a product, it's the first, x cubed, times the derivative of z with respect to x is written that way, plus z times the derivative of x cubed is 3x squared. You all with me? Okay, we're getting a little spent. Writing this out, I have 2x plus 4z cubed partial of z with respect to x plus 3x cubed y squared partial of z with respect to x. I'm just doing the distributive property. This one times this one is 3 times 3 is 9 x squared y squared z equals 0. Okay, someone help me. How are we going to get the partial of z with respect to x? What do you think we're going to do? How am I going to get the partial of z with respect to x? Here's a partial of z with respect to x. Here's a partial of z with respect to x. These don't have a partial of z with respect to x. So what we're going to do is we're going to kick everything to the one side. That does not have partial of z with respect to x. Okay, then what? How am I going to solve for partial of z with respect to x? Factor out the partial of z with respect to x. And then divide by this, which gives me partial of z with respect to x equals minus 2x minus 9x squared y squared z all over 4z cubed plus 3x cubed y squared. All right, and let me be quiet for a minute because I'm sure some of you are copying that down. Okay, so let's let that go for a minute. Okay. All right, shall we do another one? Yes. Let's do it the other way. Okay, one more time. We now want to get the partial with respect to y. I think we can do it a little quicker this time. We're differentiating with respect to y. So if we differentiate with respect to y, z changes. So you can take the partial of z with respect to y, but x is a constant. And we're going to differentiate through here because we want to get the partial of z with respect to y is what we're working towards. We differentiate each one with respect to y, but remember, x is a constant. So the derivative of x squared with respect to y is 0. Derivative of y cubed, 3y squared. Derivative of z to the fourth, since z is not a y, we differentiate with respect to z, and then we have the partial of z with respect to y. Plus, we have the constant 3x cubed times y squared times z. So it's a product rule. Y squared times the partial of z with respect to y plus z times the derivative is 2y equals 0. Cleaning this up a little bit, I have 3y squared plus 4z cubed partial of z with respect to y plus 3x cubed y squared partial of z with respect to y plus, now let's see, this is 2yz, so it'll be 6x cubed yz equals 0. My Algebra 1 teacher made you always have your variables alphabetically or she'd mark them wrong. I don't do that to you, but I'm always afraid she's going to mark it wrong on me anyway. All right, now I'm solving for partial of z with respect to y, so I leave these guys on this side. And drop kick him over there, and drop kick him over there. And since you guys are getting a little bit tired, let's do the old factor out the partial of z with respect to y by crossing it out, putting parentheses, and popping it here. And so the partial of z with respect to y is equal to minus 3y squared minus 6x cubed yz all over 4z cubed plus 3x cubed y squared. Okay, we all got that down? Okay, I'll just leave it there for a minute as people are writing it down. Okay, very good. All right, and lastly, for homework, you need to, now people, notice, I'm not saying read the whole section. I'm having you read pages 945 to the top of 953. There's a little part there I decided that I don't really want us to cover. I want you to focus on what we did on the lecture today. So just to the top, and you can see where the section's done is when you're done. And then on pages 955 to 957, you need to be looking at 3, 13 to 39, the odds, 35, 37, 41, 43, 47, 51, 53, 55, 57, 59, and 61. Practice. All right, and I'll see you next time.